Hello students, welcome to our discussion on module E on gradually varied flow. So far in open channel flow, that is up to module D, we have good discussions about critical flow, supercritical flow, subcritical flow, try to understand how they are related to Froude number and what is the relationship between depth of flow and specific energy, why we actually plot the variations between specific energy and depth of flow. Also, we looked into that what are the salient point of critical flow, that is at critical point we can ensure that transitions can take place without impacting the flow upstream of the channel sections. Then after this, we had a quick discussion on uniform flow, that what are the governing equations of uniform flow, where we talked about Manning's equation and Chase's equation. And as the name suggests, in uniform flow, rate change of depth of water with respect to x, or as we were moving horizontally, the rate change of depth of water is equal to 0. That means if this is our channel bed and water is flowing somewhere here, the depth y1 and y2 is going to be constant. And we also learned that for this uniform flow to happen, there has to be some balancing forces. That if there is a gravitational force in downward direction, it has to be balanced by the frictional force, which is exactly acting exactly opposite and with equal magnitude, as a result of which there is no change of slope. However, in real world, what happens is that when channel is flowing, it would definitely flow with some uniform depth, which is equal to yn, but it will encounter some transitions. For example, at some point, we may have a dam. Once there is a dam, there has to be rise in water. Or if there is after a dam, we will release this water and it will flow downwards. We may have some other transition where this channel from horizontal is transitioning to some steeper slope section. So, and this is very ubiquitous to all the channels or cross sections that we encounter in real world open channel flow settings. So we want to understand what is the magnitude of this rate change of depth with respect to the horizontal movement of water. We also want to understand whether water is going to rise or decrease. We want to do these things quantitatively, that is, what is the magnitude of change in depth, as well as qualitatively, that is, whether water is going to increase, whether or decrease in elevation, whether hydraulic jump is going to get formed, whether whether gradually varying flow is possible or not. So these are the questions that we will try to answer in this particular module. Also, as the name suggests, we are going to talk about gradually varied flow. We looked into example of hydraulic jump, which was example of rapidly varying flow. However, in this module, our discussions would be primarily on the gradual flow. That would mean that length of flow is sufficient enough that the water profile has sufficient time to adjust to the changes. That means that if channel is flowing, this dam is not coming up abruptly. That dam was there and now water has been flowing there for a while, and now it has reached a steady state and that profile has become apparent or clear. So to understand all these things, there are two methods to do that. One is approximate way, which we are going to adapt in this chapter or adopt in this chapter. And another one is Saint-Venant's equation, which are typically used in various hydraulic modeling softwares. In our lab sessions, we will talk about certain softwares which are used to do such kind of modeling, which includes HEC, RAS, and it solves 1D and 2D Saint-Venant equation. But these Saint-Venant equation, they are also based on Reynolds transportation theorem. We will go into details of these Saint-Venant's equation whenever we have to deal with this software HEC-RAS, but in this module, we are going to discuss these approximate solutions to this problem. And first of all, we will develop some qualitative insights that how these profiles are going to look like. Before we go there, let us try to go back to our Bernoulli's theorem, which can be written as H equal to Z plus Y plus V square by 2G. If we take derivative on both sides, we can write that dH upon dx is equal to dz upon dx plus dy upon dx plus rate change of v square by 2g with respect to x. This is rate change of elevation of water as we are moving along the flow. Dz upon dx can be assumed for channels with considerably smaller inclines, that if in such channels tan theta can be approximated as sine theta or equal to theta, and we are saying that this rate change of height of bed with respect to datum as we are moving ahead is equal to slope of the channel section. This quantity, that is rate change of total energy with respect to x, is known as the slope of energy grade line. Now you can very well expand this v square by 2g if we write v is equal to q by a, that minus sf is equal to minus s naught plus dy upon dx, and this derivative becomes q square, or third term would become plus q square by 2g into minus 2b upon a cube into dy by dx. And if we bring all the terms together and rearrange certain terms here, you would see that dy by dx is equal to s naught minus sf 1 minus Froude number square, because our Froude number is given by v root gy, and this v can be written as q divided by a, and this is of course gy, and upon rearranging you would be able to see that indeed this term is equal to square of Froude number, which I leave as a small exercise for you. And you should be able to rearrange these terms, bring all dy by dx on one side, and you should be able to write it. Now, in case of uniform flow, what happens is that this dy by dx is equal to 0. That would mean that our S naught is equal to SF, or the slope of energy grade line coincides with the slope of channel bed, or energy grade line is parallel to the channel bed. But in case of non-uniform flow, that is not the case, because dy by dx is no longer equal to 0. And sign of dy by dx is essentially governed by the sign of difference in magnitude, or difference of sign of S naught minus SF and 1 minus Froude number square. Now we have learned that determining Froude number is relatively straightforward if you know velocity, depth of flow, or geometric properties. S naught is the known property of channel, whereas SF is little tricky. And to solve this, as I mentioned, we either use Saint-Venant's equation or we develop some numerical approximations to quantitatively determine the magnitude of dy by dx. In this module, our interest is first of all to develop the qualitative understanding, and we will leave the quantitative understanding of dy by dx or using some numerical approximations as advanced topic, and that would not be covered as first part of open channel flow. So here our objective is to understand qualitative variations in dy by dx, that is under different conditions, whether depth of flow will increase, whether it will decrease, it will concave upward or it will concave downwards. So we will name these profiles, and that is what we will try to cover in this module, that how to name these profiles and develop understanding about that. But our governing equation is going to be dy by dx equal to S naught minus SF 1 minus Froude number square. Now, when we talk about S naught, we can definitely write our S naught is equal to, or Q is equal to 1 by N R to the power 2 by 3 S naught to the power 1 by 2 into A, which implies our S naught equal to N square Q square divided by R to the power 4 by 3 into A square. Whatever depth we get from this, because our R is also function of depth, our area is also function of depth, and if we are assuming prismatic channel, then we can say that width is constant throughout x, so we are not really worried about variation in width, and hence we can simply say that R is function of y as well as area is function of y. If we talk about S naught, the depth corresponding to this S naught is called as normal depth. If our depth is greater than normal depth, or depth of real flow is less than normal depth, we can safely say that our flow is no longer uniform because Manning's equation is not holding true, or the flow is not parallel, or the depth or the slope of energy grade line is not parallel to the channel bed, as a result of which there is some variation that is happening, which we get from the derivative of Bernoulli's equation. Or we can have y is equal to yn, which is indeed the case of uniform flow. And these two cases are cases of non-uniform flow where variation in depth is happening. If we do not know that in case of non-uniform flow, whether Manning's equation would be applicable as it is, but we know that we can make an approximation that instead of S naught, we can use the slope of energy grid line and say that Q is equal to 1 by N, R to the power 2 by 3, SF into 1 by A. And we say that this is an approximate equation that we can use for non-uniform flow, where instead of channel slope, we are using slope of energy grid line. And we can say that SF equal to N square Q square R to the power 2 by 3 square A square. And it is very clear that all the terms in denominator, they are function of y. So as y increases, that would mean SF will decrease. And as y increases, that means we are going above the normal depth, or y is greater than normal depth. So that would mean that our SF is less than S naught. Similarly, if our actual depth of flow is less than the normal depth of flow as we would obtain from Manning's equation, we would say that our y is less than yn, and this corresponds to the case that SF is greater than S naught. And third case, when y is equal to y naught, we will say that our S naught is equal to SF, or it is indeed a case of uniform flow because normal depth coincides with actual flow depth. So this is important because we are going to use this as a governing equation, and S naught minus SF sign matters. And that is why we have done this sort of prelogue or introduction, that how we are going to address this part of dy by dx equal to S naught minus SF divided by 1 minus Froude number square. But before we go there, let us also try to look into slopes of channel bed. We would need to classify whether our channel bed is steeper, or it is mild, or it is critical, or it is horizontal, or it is adverse. Let us try to add some meaning to that. As the name suggests, that steeper slope should have large magnitude of inclination, but how we should relate it to the quantities that we have already learned. So first, we can always calculate the critical depth YC associated with some discharge Q. And if we know discharge Q and we know G and width, we know that our Froude number is equal to Q divided by A multiplied by Y, Q by A into root of GY. So we can always solve this equation because at critical depth Froude number is equal to 1. So the YC that we will get would correspond to our critical depth. Similarly, we can calculate normal depth using Manning's equation, and we have already understood the use of these charts, how we can solve Manning equation using some design charts, or the three methods which include hit and trial, numerical approximation techniques, and finally the design graphs that are available to us. So it is very clear that if this channel slope is steeper, then water would have tendency to flow faster. If water has tendency to flow faster, that would mean that depth of flow, specifically normal depth of flow, is going to be lesser. And we can say that we can use this criteria to say that if our normal depth of flow is less than our critical depth, that is yn is less than yc, that would mean that our channel bed is steeper, or we say that channel bed can be classified as S. Let us move to second case. If S is clear, if we have a channel bed where our depth of flow yn is greater than our critical depth of flow. That would mean since depth is considerable, flow velocities would be lesser as compared to the steeper channel. We can use this definition to call our channel bed as M or mild if our normal depth of flow is greater than YC. Finally, we have the third case where our channel bed is such that the critical depth that we determined from formula of Froude number and normal depth that we derive from Manning's equation, they have exactly same value, and we say that this is equal to this channel bed can be classified as critical or represented by letter C, critical, where critical depth is equal to normal depth of flow. So that covers our steeper, mild, and critical. Now, what is this horizontal flow? So sometimes what happens, and we have also looked into some examples of this, that is whenever we have a reservoir, we will have some water coming, and for certain depth we will provide the after shoot we will have this basin, which we also call as stilling basin, where there would not be any significant slope, and we would let hydraulic jump formation to start from here, and this stilling basin would have almost zero slope, and we will say that when slope is equal to zero, our profile is going to be horizontal. Needless to say, this particular profile, it is hard to sustain because water cannot flow on horizontal surface unless there is a constant velocity head that is present throughout to push that water. Hence, we would have limited encounter of horizontal profiles. Then we also have adverse profiles. Theoretically, we can have a channel like this where water has to go against the gravity and climb up. And as you can imagine, both these scenarios where we have adverse slope or negative slope or horizontal slope, they are going to be rare encounters. So the most common encounters are going to be our steeper slope and mild slope, whereas critical slope is also just 1 point because yn has to be equal to yc exactly. If it is slightly greater, we can say that, oh, since normal depth of flow is greater than critical depth of flow, it can be classified as subcritical. So we can go it as with a mild slope classification and so on. So steeper and mild, they are going to be our most common candidate, whereas critical slope will help us understand certain phenomena. So with that, we are good to start classifying the sign of dy by dx, which is given by S naught minus SF divided by 1 minus FR square for various channel sections, which would have M, which would have S, which would have C, H, and A as their first letter representatives. And we are going to understand in different scenarios what kind of profiles we can expect and what would be the change in dy by dx for those profiles. Thank you.